In this lecture, we're going to spend some time looking at some basics related to absorption spectroscopy. So, how does absorption spectroscopy work? Okay, so first of all, let's remind ourselves what we're talking about. So, spectroscopy, study of light interacting with matter. And then matter is stuff with mass. Hate to reduce this definition too much more, but that's what we need to worry about for understanding this lecture. So what we have is we have light now, and we have light interacting with stuff with mass. If you recall, light is massless stuff moving at the speed of light. Okay, where the speed of light is labeled c, and that's just the speed of light in a vacuum. Okay, so this is a constant, c is. That's why we label it c as opposed to another variable notation. So light can be considered a particle or a wave. So in addition to being massless and moving at the speed of light, just some basic physics, light can be thought of or treated or kind of considered in terms of its physical properties as a particle or a wave. Now, it's this wave nature that can be really helpful, especially in spectroscopy. And so if we have a wave, we have to think about what's called wave mechanics or wave physics. And so wave mechanics, which is really how do waves work? If we wanted to understand waves, what properties do they have? So to do this is one of these things where I feel like we could make harder than we need to, but let's just focus on what we need to do, what we need to know to really understand spectroscopy to the degree that we want to understand it. So I'm going to draw a wave, and I'm having a wave propagate along an x-axis, just kind of moving up and down about a y-axis, and then I'll run out of paper here. Okay. So there are some things I want to first note. If you start at a point on a wave and you sort of traverse that wave through an entire up cycle and an entire down cycle, and you get back to the original spot after going both up and down, we call this a period. So this is the period of a wave. Now, what's important is that the period of a wave should be constant whether you're starting from an origin and you're going up and down, starting from an origin and going down and up. That should be the same distance. Or I'm going to mix my colors here a little bit. If you decide you want to start from a different random point, as long as you go all the way up and all the way down, that will constitute a period for the wave. Okay, so a period is just starting from somewhere. We usually think about the origin. It's a pretty easy starting place, moving all the way up, all the way down, back to the original position. Okay, so let's go ahead. I'm going to turn the page and let's write some words now. So the period is going from some point. Usually we start at a 0. So usually a 0 point. Now, interestingly, we call the 0 points nodes, and that might be a helpful term to hold on to. So we go through some point, and I like to write through a full up and down cycle, and we could go in either order. So you could go down first and then up. Through an up and down cycle back to the same Y position, which again is usually 0. Okay, so that's a full period. Now, a wavelength is related to this. This is the distance of an entire period of a wave. Entire is kind of a bit redundant. If we're talking about a period, we have to go through that full up and down cycle anyway. Okay, so the wavelength is that distance for a period. And so if we had just a small wave and we consider starting from node going positive first and then negative, going through an up cycle and then a down cycle. Let's assume that that's a nicer symmetrical wave. The horizontal x distance is the wavelength. Now the wavelength is not spelled correctly. Let's get that right. The wavelength is labeled with the label lambda. So lambda looks like this, and I would take a second to get good at drawing a lambda. So that's an important property of a wave, is the wavelength, okay? And to understand the wavelength, that's why we introduced that term period. Now, another term that's useful, that's really critical to understanding wave mechanics, is the idea of a frequency. So frequency is another term worth highlighting when you're studying wave mechanics. And that is the number of periods that occur per unit of time. Okay? And this is labeled with what looks like a V with a tail. This is actually nu and u. So we want to understand lambda and we want to understand nu. So the typical units for nu are per unit of time. So it's 1 over time. Now the typical, those are the units. I guess the typical general, even SI units are the hertz, H-E-R-T-Z, and that's named after a physicist, so we'll capitalize that, I suppose. And that's a per second, so 1 over 1 second, or a second to the -1 power. Okay, let's look at some examples of waves. I'm going to turn the page in a second, so pause if you need to. Let's look at some examples of waves with different wavelengths and frequencies to make sure that we can grasp these topics more fully. So let's have I'm going to be kind of careful. Take a second, focus on drawing some good waves. Okay. Trying to draw these waves, you can probably see what I'm doing here. One that's more frequently propagating, one that's appears to have frequency is a nice term to use, but they're all propagating at the same speed. Anyway, let's get into it. Okay, so we have wave A and we have wave B. I tried to make them so they're kind of going up and down at the same amplitude or the same distance along the y-axis, but that's easier said than done. Okay, so what we say is if we look at these, we first of all could consider a period from, I usually start from the node or the 0 point and go to another 0 point. Remember, we have to go both through an up and a down cycle in either order. Anyway, this distance from dot to dot is the wavelength of A. Conversely, we have the wavelength of B, and now looking at this right away, we can say that wave A has a, let's compare. What I want to do is consider longer or shorter wavelength than that of B. So wavelength, recall, is lambda. So if we look at wave A, would we say that wave A has a longer wavelength or a shorter wavelength than B? We would say longer. That distance of the yellow line is much longer in the case of wavelength A than the case of wavelength B. So we've looked at one property, the wavelength. What about the frequency? If we consider the frequency between, compare the frequency of both of these two, we would say that wave B has a, I'm going to leave a blank here. We're going to go for lower or higher frequency. Oh, wave A than wave B. So if we compare the frequency of wave A and wave B, that's the number of periods that occur per unit of time. So if we consider the x-axis to be a constant unit of time between both of these, that is, if I say that a different way, I'm going to delete this highlighting. But if we look at the green line, we'll say the green line in both cases is equal distance, and the x-axis is indeed time. Should perhaps label that. Well, no, because sometimes we want that distance to be a distance. Okay. So if we consider wave A and wave B, and the x-axis is consistent, what we notice is that wave A goes through 1, and then we go through 1 period, 2 periods, 3 periods. Now, because the timing is consistent, even though we don't know what that actual duration of time is along the x-axis, because the timing is consistent, we can just compare that with wave B through 1 wavelength, 2 wavelengths, or 2 periods, 3 periods, 4 periods, 5 periods, 6 periods. Six periods. Okay, so if we look at this, we could say that wave A has a lower frequency than wave B. We went through 3 periods versus 6 periods. In fact, we could even quantify this and say that wave A has, or we could, let's put it in the context of wave B because that'll be less awkward. Wave B has a frequency twice as high as wave A. Now, one thing we didn't really, I'm going to leave this up here. One thing I want to look at before we break for this is we could say I didn't prescribe a unit of time, so I can't put these units into hertz, but because the unit of time was consistent, we can count those frequencies over that entire duration and get some idea. Now, one thing I was trying to be careful to do was to get to a point where the frequency was double of B was double that of A, which we've achieved. So wave B has a frequency that's twice as high as wave A. Now, what I want you to notice is that if we draw a dotted line, let's see how good of a job I did, from one period length, oh, I didn't do great, but let's just cut this here. If I draw a line connecting one period length of A, and I match that to the wave for B, we got pretty close. My drawing was a little off. We got pretty close to hitting 2 periods within that first wavelength. Now, what I'm trying to show here is that not only is the frequency of B twice that of A, but it's also the case that the wavelength of A is twice as big as the wavelength of B. There's a linear relationship. The wavelength of A is twice as high or twice as long. It is a unit of distance. As the wavelength of B. Okay? Now, there's a few things I want us to recognize before we break. The first is that wavelength and frequency are inversely related . Not only are they inversely related, they're inversely related by a linear relationship. Now we'll look at this mathematically. Because it's a linear relationship, the mathematics are not challenging. But this is a critical idea I wanted us to take away from this little exercise. Wavelength and frequency are inversely related. As one increases, the other must decrease. But not only that, but they're inversely related by a linear relationship if we do a good job drawing our waves. And we'll look at the mathematics of this and see how this all fits together utilizing the speed of light in a future lecture. But we want to keep this in mind. As the wavelength gets larger, the frequency will get smaller by a proportional amount. Okay, so with that, we'll break for this lecture. We'll pick up with more of this in the next lecture.